Hello and welcome. Today we're going to take our exploration of floating points a bit further and start talking about the fractional part after the decimal point. Along the way, we will talk about passing strings from basic to assembly, the string descriptor, and hijacking the basic parser to do temporary evaluation. If you haven't seen the floating point intro video, what are you doing? Why are you watching them out of order? The titles are very clear. They're uploaded in a specific order. The thumbnails tell you which is the intro and which is the next one. I don't understand. Let's start with the basic code. So most of this is exactly the same as in part one. All these subroutines are exactly the same. The only thing that's changing is how we're determining what to actually convert. Rather than having a for next loop that will loop through a bunch of integers, we allow the user to enter any decimal number, any string. And then to call the subroutine, we got to do this funky thing. Rather than directly passing the parameter to the assembly language subroutine, we pass VARPTR. This gives us the address of the parameter because we cannot directly pass a string, but we can pass the address of the string. And then inside the assembly code, we can use that to get to the actual characters. So let's take a look at what this would give us. What would the address of a string actually point to? The string descriptor is pretty simple. It's just 5 bytes, and 2 of them are dumb. So the very first byte, byte 0, gives you the length. How long is the string? Then you skip this dumb byte, and then you get to these 2 bytes that just point you to the address of the characters. So really all we need to do is look at the length, and here grab the address. So this address would point to just a list of characters one after the other after the other. So there's nothing really all that interesting about this. So that's it. So I know how to get my string from basic to assembly language, and I know how to access the characters of that string, but how do I actually convert that string to a floating point number and get that stored in the floating point accumulator? So it's back to the Unravelled book where they tell you how everything is implemented. And basically what I want to do is what val, the basic command val, does. So I took a look at val and ended up copying pretty much all of it directly into my code. The very first part of val assumes it can get x to point to the string. So the only code here that I had to write myself is code to make sure that x points to the string. Otherwise, I kept this pretty much intact. So let's take a look at what I did. So the code starts off with some well-known addresses of either memory or routines that I need to call. Some of this you may recall from part one. In fact, all of this code from part one I'm keeping, and I'm just not calling it. So there's some code here that begins at address 3F100 that I'm now leaving alone, although I will be making use of this do copy part. This copied the floating point accumulator to my memory. So you see a return here, and that's okay because we're not actually starting there. We're actually starting here. So the first thing I do is I call the getArg helper, and that makes sure that the D register points to the parameter. And remember, the parameter is the string descriptor address. So D is now pointing to the string descriptor address. And now X is pointing to the string descriptor address. So the next thing I do is I grab the length. So this gets me into X, so it points where X is pointing. And this gives me that byte 0 to give me the length. So B is now the length. And then I skip 2, so now I'm pointing to the address of the characters. I'm adding 2 because we got 1 for the length, and then we got 1 for the reserved byte. So now my X is where it's supposed to be, and I can shamelessly copy val. So every time you see like a comment with all caps, you know I just copy pasted that directly from the Unravelled book. So whatever this stuff is doing, it should be properly converting the string that x points to into the floating point accumulator as a floating point number. When it's all done, here's me again. I go to my copy routine from last time to copy the floating point accumulator to my copy of the memory here so that BASIC can access it safely just like it did last time. And that's it. We should definitely step through some of this in the debugger to make sure it's working and to help us understand how it's all laid out. Alright, let's run our new BASIC program. And let's try something simple like 1.2. So we've hit our breakpoint at the beginning of my new routine, so let's remind ourselves what that code is doing. So we're here at 3F20. First thing we're going to do is get the string descriptor into D. So let's step that. And then let's take a look at our D. So our D is pointing at 2ADA. Let's see. So the first byte, the 0th byte I should say, is the length, which is good. 1.2 has 3 characters. That's reserved. And then here is the address of the characters, 3EFC. So let's take a look at that. And sure enough, we see 1.2. By the way, that also uses a point for anything that I guess is unreadable. So we should probably double check that 2e is really a decimal point, but I have faith. I'm just going to assume it is. What's the next thing we do? We transfer into x, we put the length in b, and then we repoint x at the address. Let's make sure that worked. Okay, x is now pointing at 3EFC. Very nice, exactly where it should be. What next? Next we do all the stuff. We call all this stuff. So what I'm going to do is wait until I get to this jump at the, I'm going to skip to that jump and see what ended up happening. So this is that jump we're going to go to. That does the copying. So I'm going to hit F5. And that should have done all of the conversion for us. So let's actually take a look at the accumulator and see what it has. The accumulator is at 4F. And so here is that right? I don't know. Is that right? I don't know, but I guess we're going to copy it to our memory and then we're going to print it out. I guess let's just run it and do that. Boy, that's complicated. 1.2 looks really complicated. Huh. I hope the code is right. Let's try something that should come out simple. If a power of 2, let's actually do an integer, power of 2. And I'm going to actually turn off my breakpoint. Alright, that looks about right. We've got a nice single sole bit here, and then we have a nice exponent that probably looks like it'll get us up to 256. So if I have a power of 2 after the decimal point, surely that would also be simple, right? Ooh, not simple at all. What about just 0.2? Goodness gracious. What would it take to get a simple number here, or is my code all wrong? Alright, let's talk about what's going on. The floating point accumulator is going to be storing a number something like this. This is just one example. So every digit is just a bit, and there will be a decimal point, and then more bits after the decimal point. So as we talked about last time, to the left of the decimal point, you just go up by powers of 2. So this would be 1 times 1, 2 times 1, we skip the 4th place, we skip the 8th place, and then we add 16 times 1. That gives us the integer part. After the decimal point, it's the same thing, it's just negative powers of 2 instead of positive powers of 2. So a 0 here means we have 0 halves. A 1 here means we're adding 1 quarter. We're skipping the eighths, but we're adding 1/1/16. So if our goal is to get something simple, something that doesn't require a whole lot of digits, the best thing to do would be to just try a negative power of 2. So let's say, 1/16. So let's actually try that with my code. Let's type in 1/16. And we should expect to see just a single bit set. And then the exponent will take care of the rest. 0.0625. Ooh, that is encouraging. Okay, so we have only a single bit set in our mantissa, and notice that our exponent is less than 80. How far less than 80 is it? It's 80, 7f, 7e, 7d. So this is 2 to the negative 3. And remember, we kind of assume that the decimal point is right here to start with, just before that first bit. So if we shift it to the left 3 more times, we end up with this. The point was here, and we went boop, boop, boop. And so we have 1/16 sitting there. Okay, so let's say we add another bit in here. What if we added in an eighth? That would be 0.1875. 2 bits! We get 2 bit sets! And then we move this far to the left. Perhaps the code works perfectly fine. One thing to point out is that to keep as many digits of precision as possible, things get worked out so that the opening bit of the mantissa is always set. In other words, you can use the exponent to make up for stuff. You can use it to shift to the left or to the right as much as you want. But if you started off with a 0 here, you would be losing in the rest of these some digits of precision. Why do that? Why not just always start with a 1 so that everything after here is a required part of the number? And then the exponent just makes it up. So for example, if we tried something more complicated, which we thought might be simpler, or at least I thought might be simpler, by having the 1 here, we get to use as many digits of accuracy, of precision, as we possibly can. As a final segment, if any of you were curious what this code does that I copied from the Unravelled book, I have like inklings, and I'm going to kind of run through what I think is happening. First of all, you might have recalled that I loaded the B register with the very beginning of the descriptor so B would have the length. I never said why I did that. Well, the code that I copied assumes B will be the length, and it assumes X is going to point to the beginning of the string characters so that it can add B to X and then clear that out. So the idea is that you want whatever is at the end of the characters to be null. So it's kind of like a string terminator for the Coco ROM, kind of like you would see in C. The other thing that's going on here is this seems to be hijacking the basic parser. So the basic parser, it looks like, I think, that char add, this address, tends to point to the next character that's going to be read in by the interpreter's parser. And so we're kind of hijacking it. We're saving it away, like from what it used to be, and then we're sticking X there. So we're kind of making it look like that's the next thing to read. And then what do? We read it. So we go here and we get the next thing out, and then I think maybe this is going to assume that the rest is going to be continued to point there. So this code here does the main work, and then we just saved and restored the registers on either side. And then we just fixed stuff up at the end. So all the stuff that we did to hijack, we unhijack. And then, of course, my line, which does the copy. That's what I think is going on, but I found it kind of interesting that the Coco ROM will use itself in ways that it wasn't originally intended to be written, or maybe it was intended to be, but it was mainly there for the parser. But then it just kind of reuses the parser by this little hack to put characters that it needs to read where the parser would normally expect them from the line. Anyway, that's all for today, and that's all for Floating Point. There will be more assembly adventures to come, and I will see you next time.